So now let us see the construction of an LR parsing table. So for that we need to know about LR0 item, or simply it is an item. So it indicates how much of a production is seen from the input buffer at a particular point. It is represented using productions with a dot at some position in the right side. Let us see an example for this, that is A gives XYZ. So there will be 4 items associated with this particular production, that is A gives dot XYZ, A gives X dot YZ, A gives XY dot Z, and finally A gives XYZ dot. So the meaning of say we are checking this A gives dot XYZ. So here we are about to see those sequence of terminals which could be derived from A. We are expecting to see those terminals which could be derived from this particular X, Y, Z, this sequence of symbols. So when you say X, Y and Z, X is a single non-terminal or terminal symbol, okay, and Y also the same. In the second item, that is A gives X dot YZ, that means you have already seen those sequence of terminals that could be derived from X, and you are hoping to see those sequence of terminals which could be derived from YZ. So here also the same, this A gives XY dot Z, you have already seen from the input, you have already seen those sequence of terminals which could be derived from XY, and you are expecting to see those sequence of terminals which could be derived from the symbol Z. So when you say XYZ, it can be a terminal as well as non-terminal. Here this last item, that is A gives XYZ dot, here you have already seen those sequence of terminals which could be derived from XYZ. That means the whole of XYZ is whole of XYZ is seen, means you are about to, you can now reduce it to A. So those sequence of terminals which could be derived from A is already seen from the input. That is what this item means. So when you have dot on the right end, that means you can reduce this sequence to the non-terminal left hand side of this production A. So for the grammar that you are discussing about for constructing the parsing table, you can construct a deterministic finite automaton, that is DFA, from the grammar. So you will be constructing a DFA with so DFA means you will have states, and how these states are constructed, that is what we are going to see. So you have productions, or you have items associated with those productions, and those items can be grouped together in a particular manner into different sets, and those sets are the states of this particular DFA that we are discussing about. So these states can be formed using grouping together of those items with respect to productions. Now, collection of sets. So since we have so many groups of items, so all those groups of items with transitions can be collectively called as canonical LR0 collection. So for constructing this canonical LR0 collection, you need to have an augmented grammar, and you need to use two functions, closure and goto. Now let us consider an example grammar for construction of this parsing table, and subsequently tracing out an input with respect to this grammar. Okay, let us consider this a grammar G. So you have two productions, S gives ASB and S gives B. So these are the two productions. Now you need to transform this grammar so that it will be more easier for constructing the parsing table. So here for that you will be having an additional production with, actually for this particular grammar you have S as the start symbol, so you will be adding a new production with S on the right side of that production, and on the left side you will be having a new terminal. So how you will do that, we will see here. So it is the new production S dash gives S, and the purpose of adding this production is to have for a particular bottom-up parsing method, basically what we do is you will have an input string and you will be reducing it to the start symbol of the grammar. So here when you have a string, that will be reducing, it will be getting reduced finally to the start symbol yes. The purpose of adding this is you are about to reduce yes to s dash, which means accepting. So whenever you get to a point where you are about to reduce, you have got yes and you are about to reduce to the left side, that is s dash, that means you can accept that string. So just to have that acceptance of the input, you are adding this new production. So the other two productions, s gives ASB and s gives B, will be there with this, and you can call this new grammar with these three productions as augmented grammar G dash. Now let us start considering the items with respect to this particular augmented grammar. So we are going to construct the canonical LR0 collection of these items. Okay, so to start with, we will be considering the first item of this with respect to this the production s dash gives yes in the augmented grammar. So the item is s dash gives dot yes, so dot at the left end. Okay, so now this is the first item that we are considering. Now you need to find the closure of this particular item. So what is the closure of an item? So for an item, the dot will be present somewhere, so there will be some symbol on the right immediately succeeding the dot. So here we have a non-terminal s which is succeeding it. So to find the closure of this item, you need to have all those productions you need to consider with this non-terminal on the left side. That is, in this case, s is coming immediately after dot, so you have two productions with respect to yes as s on the left side, that is s gives ASB and s gives B. You need to add these two productions, the items with respect to these two productions with dot on the left end, that is s gives dot ASB and s gives dot B need to be added as part of finding the closure of this particular item. So you're adding it here. So you have these two items added. Now to find let us consider this to complete the closure, let us consider this item. So here after dot there is one terminal symbol coming, that is a. So there are two cases for every item to find a closure. One is having the non-terminal immediately after the dot and having a terminal immediately after the dot. So for non-terminals, as we have already done, this is the case, and for terminal symbols, this is the case A and B. So whenever a terminal comes immediately after the dot, you don't have to do anything as part of finding the closure. So there will be action performed only when you have a non-terminal immediately after the dot. Okay, so now you can group together these three items into one to make it a state, that is the initial state of the canonical LR0 collection or the DFA that we are going to construct. So that is, the state name is I0. Now you can have transitions on this particular state. All states of a DFA will have transitions. So here you will have the transitions. The transitions are determined based on the symbols succeeding the dot in for these items in this particular state. So you have here yes, that is non-terminal, and you have A and B terminals. So let us first have the S transition. So how a transition mean for an item? That is changing the dot symbol to precede it. That is, the dot will be changing. Dot will be transferred to the space where you have immediately after that particular symbol. So that is, here in this case, after S transition, it will be, this dot will be changing to the right side of S, that is S dash gives S dot. Okay, so since the dot is coming at the end, you cannot have any more items added as part of closure of this particular group. So you can finalize this group of items and name it as a new state, that is I1. Now for I0 you can have two more transitions, that is for terminal A and terminal B. So let us consider the transition A. So here after A transitions, this dot will be changing to the right side of A, that is S gives A dot SP. Okay, so now let us find the closure as we have done for I0. Let us find the closure. There is a non-terminal immediately coming after the dot. So this is since this is a non-terminal, you have to add all those productions with S as on the left side with dot on the left end. That is S gives dot ASB and S gives dot B. Now you cannot add any more because for these items you have terminals coming after the dot, so you can group this into a new state, that is I2. Now let us consider the transition B for this particular state, that is that will be the new state, that is this dot will be changing to the right side of B, so that is S gives B dot, and you cannot add any more items as part of closure for this particular item, so you can name it as a new state I3. Now first level is over. For I0 you have these three states, and for I1 now let us consider the next level, that is for I1 what are the transitions you can make. Since we have already discussed that this new production is added to identify the point where you can accept the state, that is when you are sure that you have reached yes, you have seen those sequence of terminals which can be derived from yes, you can accept it. So this is the point where you have seen the yes. So S dot means you have seen yes, the whole sequence of terminals you can be derived from yes, and you are ready to accept it. So the only transition, this is a special case, this I1 is a special case, the only transition possible here is to have an acceptance. So that will be done using the terminal symbol $, and you will accept. From here it is on $, it will be accepted, that is a state, acceptance state. Now let us consider I2 similarly. So for I2 you can have yes, A and B transitions. On yes you will have S gives AS dot B, and what are those there cannot be any more items that could be added, so it will be you can finalize it with state as I4. Now the other transitions are A and B. Just see this, S gives dot ASB, it is similar to here in I0 we have S gives dot ASB. So here on A it went to I2, so here also it is the same scenario, so you should have a loop for A transition, because from I2 on A it goes to I2 itself. Similar cases with B, the terminal B transition, that is from I2 on B you reach I3. Now let us consider this I4. So for all these, okay, for I3 also you have to be considered, but here since it is a dot is at the right end, you cannot have any more transitions. On I4 you can have one transition, that is B transition, so that gives you S gives AS B dot, and you cannot have any more transitions there, so that is the new state I5. So this is here we cannot have any more transitions in any of these states, so you can finalize this as the canonical LR0 collection of items. So this is the final for this particular augmented grammar, this is the final set of canonical collection. So this is the DFA with all these state. I0 is the initial state, and S dash gives S dot. The I1 is the final state where you can accept it.